Hi, my name is Christopher Stieg, and I'm here to spread the word about an exciting upcoming workshop at CoSyNe 2024 on Tuesday entitled Understanding Neural Computation Using Task-Trained and Data-Trained Networks. Dr. Chetan Pandaranath and I are organizing this workshop to call attention to exciting new developments in our understanding of how computations are built in the brain, and hopefully to give researchers the tools to push our understanding even further. One of the primary problems for neuroscience today is the disconnect between what we hope to understand about the brain, its underlying computations, and what we can actually observe from the brain, the neural activity. Recently, however, a new theoretical framework has built a bridge that can link between these conceptual levels and potentially let us actually understand what's happening in the brain. This framework is known as neural dynamics. Neural dynamics are the underlying rules that describe how the state of a neural system evolves over time. For instance, we could record neural population activity from a person's brain while they perform a task, and by observing how the neural state develops, we can infer a set of dynamical rules that provide a holistic description of neural activity. These neural dynamics have been shown to give insight into the complex computations performed in artificial and biological circuits. Our workshop brings together the two principal methods for using dynamics to bridge from neural activity to computation. Assume there is some ground truth computation that's being performed that we want to determine. The first approach assumes a task and trains a dynamical model to perform that task. The experimenters can then examine the learned dynamics of the model and compare simulated activity to the brain to see if there's a match. The second approach, a model called a data-trained model, learns dynamics that can reconstruct neural activity. By inspecting inferred dynamics, we can try to infer the computation that those dynamics perform. In our workshop, we're bringing together some of the leaders in task-trained and data-trained network modeling to connect these approaches and hopefully lead to new insights into how the brain performs computation at multiple levels. Specifically, we have Drs. Chetan Pandaranath and Sergeant Ostowich here to talk about their work to make data-trained models more interpretable. We also have Dr. Tatiana Engel presenting recent work from her lab on dynamics in premotor cortex. We're lucky to have Dr. David Susillo, one of the early pioneers in task-trained networks, here to talk about recent work from his lab on Dynamo, a method to compare the computational principles learned by dynamics models. We also have Mitchell Ostro, a graduate student in the FEAT lab at MIT, here to walk us through how to use his new method of comparing dynamics called dynamical similarity analysis on simulated neural data during our interactive coding tutorial session. We're also excited to hear more about the future of dynamical models with Dr. Kanika Rajan, presenting her progress on extending these models to capturing multiple interacting dynamical systems, which are likely more biologically plausible than single compartment models. Finally, we're presenting a tutorial of a new computation through dynamics benchmark, which uses task-trained models to simulate neural activity and provides benchmark datasets with known ground truth dynamics. We hope that these datasets standardize how we assess the performance of data-trained models and can serve as a test case for inferring computation. With help from David Zoltowski from the Linderman Lab, we're working to integrate a collection of benchmark models, including standard SAE models, LFADs, and JSLDS. In the benchmark, we have simulated neural activity from a range of tasks, including simple 3-bit flip-flop, a multitask network based on the work from Laura Driscoll, and a complex musculoskeletal control problem based on MotorNet from Ollie Kodal. Each task has a known ground truth dynamics and computational goal, which will allow researchers a variety of different test cases for their models. We're very excited for our lineup of presenters. In the AM session, we have Drs. Ostowich and Pandaranath presenting their work on new advances in model interpretability, and Dr. Tatiana Engel talking about her work to understand the premotor cortex, followed by a panel discussion on bridging between task and data-trained networks. In the evening, we have Drs. David Susillo and Rajan speaking about their work to compare across models and extend them to multiple interacting brain areas. We also have an interactive coding tutorial to debut the Computation through Dynamics benchmark, featuring Mitchell Ostrow to talk about dynamical similarity analysis. We're very excited to share the workshop we've organized and look forward to seeing everyone in Portugal.